السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, this lecture, I hope, we will be done with Perceptron. Inshallah, we'll start with a new session next Sunday, which is a very important session, by the way, the next session. We were talking about Perceptron, and the last thing that we did, I think, in the last few minutes last time, was some practical considerations. So we mentioned three things. The first one was the order of training examples. And we said that, of course, because we are updating the model with every mistake, and with every new example we might update or might not, then the updates of the model will depend on the order of the examples. Okay? And we mentioned that the best thing to do is to randomize the order of the examples. We can do that, which we call it shuffling. We can do that at the beginning, once at the beginning of the algorithm of training, or even better, to do it at the beginning of every pass on the training examples. So that was the first thing. The second thing also that we discussed last time was early stopping, or where to stop, or when to stop going through the training examples. There is, of course, a hyperparameter that's called maximum iteration, and we discussed last time how we can tune this parameter using the dataset. I think you remember the plot that we had. So we discussed that. Of course, we need to do that to avoid overfitting. Otherwise, we will keep passing through the data, and that might lead to overfitting. The last thing that we started to discuss was that with Perceptron, for prediction, we only keep the last model that we learn. Remember, in Perceptron, we keep updating, right? Whenever we make a mistake on predicting the label for any of the training examples, we change the model. We change the weights and we change the bias, which means that we change the model. Eventually, the model that we will use in prediction is the last model that we learned. Okay? Now, imagine with me that, let's say that we have 1,000 examples. We kept changing the model in the first 100. And then the model kept stable without any change for, let's say, up to the example 999. So it survived very long time without any mistakes. Does that indicate that the model is good or bad? It's good enough, right? It survived. It made correct predictions for so many training examples. But then at the last one, it made a mistake. So we had to change the model, right? Why is that bad? Because the model just changed it now right away, and we are not sure if it was as good as the previous one or not, right? So the previous one is gone. We don't keep it. We don't keep even any of the previous ones, even if they survived for a long time, even if they were fixed for a long time, which means actually that they were good to correctly predict the label for so many examples. But at the last example, we changed the model, so the previous model was gone. That's a disadvantage of the vanilla Perceptron algorithm, that we only keep the last model. We don't keep any intermediate models that we learned over time. With that, we have two solutions. One is called voting Perceptron, or voted Perceptron, and the other is averaged or averaging Perceptron. So we'll discuss these next, inshallah. What do we mean by voted Perceptron? We just mentioned that some of the models that we learned over time might have long survival time. They might be correct for many training examples. And some might not be that good. It might be correct for one or two examples and then change it again. Okay? So we want to make use of all the models that we learned over the training phase. How can we do that? We will actually store those models. What is the model that we want to store? That's just the weights and the bias, right? So whenever we have a new model, we store it. Weight and bias, weight and bias, weight and bias. But with every model, we also store how good it is. How can we indicate how good the model is? By the survival time, what we call the survival time. the number of examples that were correctly classified with that model. So as that number increases, that means that the model was stable for a long time, was good for a long time. It was able to correctly predict the labels for many examples. So eventually we'll have something like this. Let's say that this is model 1. And maybe model 1 was there for 3 examples. After the third examples, it made a mistake. So we got a new model. Changed M1 to get M2. Okay, M2 survived for 10 examples. Then updated to M3. M3 survived for 5 examples. Then M4 survived for 35 examples. And so on. Okay, maybe the last one, let's call it MK capital here, survived for 212 examples. Okay? What we do in vanilla Perceptron is that we use only this one, right? In predictions. We only get the opinion or the prediction of this model only. We don't use any of the previous models. In voted Perceptron, we'll get a voted prediction. Every one of these models will have a vote on whether this model should be positive, this example should be positive or negative. Type. All the votes are equal? No. We will weight every vote by the survival time. So this is the model, number I, and this is the survival time for model I, which we call it CI here. Okay? So we will get, in prediction, we will get the prediction of M1. We multiply it. So the prediction of M1 or any model will be either 1 or minus 1, positive or negative. Okay, we'll assume here that it's 1 or minus 1. So we will, whatever the prediction of M1 is, we will multiply it by 3. And we also check M2. We get its prediction multiplied by 10. M3 multiplied by 5. M4 multiplied by 35. MK multiplied by 212. Then we sum all of these numbers. Okay? So this is like allowing every model to say its opinion or its vote or its prediction, but it will be weighted by how good the model is. And then we get the sum of all of these. This is exactly what we see here in the equation. Okay? Where is the prediction for each model? This is the prediction for model number K. Because the prediction, if you remember, we are given an example. We want to get the predicted label for it. We multiply it by the weight and we add the bias. And then we get the sign. Remember the step function after the weighted sum? We get the sign, which is the predicted label. So this is the prediction of model number K. Now we multiply it by the survival time of that model. And then sum over all models. So here we assume that we have K capital models. After we multiply, after we do all of this, after we do all these summations, we will have either a positive value or a negative value. So we get just the sign to be the final predicted value or final predicted label for this example. So that means that we involved all the models that we learned over time in the prediction. It's not just the last one. In vanilla Perceptron, we just use the last one because that's the last learned model. Okay? Here we use all intermediate models, even the first one. Okay? And each one will be voted by its goodness, its quality. Okay? Measured by how many examples were correctly classified using this model, which is the survival time, because the model will survive until it made a mistake, right? At that point, we will have an updated model. Okay, is that clear? Yes?
Each model starts from the beginning or from where the previous model stopped?
No, all of these models are from the beginning of training. We keep all the models from moment number 0. Okay? Any other questions? Type. How many models? Are we sure how many models we will get? No. Where should we stop? Or when should we stop? Based on the number of iterations, right? Whatever the number of iteration is, we will get all the models that we learned so far. Type. Every model here is a hyperplane, right? We mentioned that the model learned by Perceptron is a hyperplane. So every model here is actually a hyperplane. But they are different, of course. Okay?
For Naima's question, like, what do you mean, not from the beginning? Why?
No, we said that all the models from the beginning.
But when we create a model, the first model is created using the first one of the examples.
Yes, whatever.
Then we add another example. So
We got a new model, we store it.
Yeah, so it's like completing on.
Yes, all the models are extension of the previous models, yes, but they are different. Eventually they are different. So we will get the opinions of all of them. Okay, is that clear now? Is this new, this is a new algorithm now, right? Because we did some changes now to both training and prediction of vanilla Perceptron. What did we change in the training? Did we change anything in training? We just saved the models. For every model, we save it, and we also save the survival time for it. Okay, just a counter. That's the only change in training. Do we change anything in computations? Or no, it's exactly the same model, the same algorithm, except that we are storing the models over time. Type. Do you have a question?
Yeah.
Yes.
Survival time comes from the development set.
No. From training.
Okay. Can you use accuracy instead of survival time?
It's the same indication, right? It's the same indication, exactly. They are relative to each other. Yeah. Yes.
The last result, the sign of
The last result, you mean the predicted label, the final predicted label for the given example.
after the summation.
Yes.
Will the sign decide whether the model was good or bad?
No, the sign is to get the actual label. Okay. Here, what will be the value of this part, of this factor? It's either +1 or -1, right? +1 or -1. Now we will multiply that by the survival time. So it will be a bigger number. And survival time is just an integer, like the numbers that we have here, right? 5, 10, 35, and so on. So they will be bigger positive numbers or bigger negative numbers or small, whatever. But then we sum to see, is the sum positive or negative? Because if the sum is positive, that means that the majority vote at the end, or the aggregate vote in the end, is positive. So the decision should be positive. Okay, so just take the sign at the end to determine the final prediction. Is that clear now?
Yeah. That's right. The final will have multiple models or all of them?
We're getting back to that now. So in training, we said that we will just store the model and the survival time for each model. Type. What do we do in prediction? Previously, we were just using the final model. We are doing this operation, this computation only to get the predicted label. Now, instead of that, we are doing it for every model. In the vanilla Perceptron, we do that once for the final model, right? Now, we need to do the prediction from each model and then aggregate it this way. We multiply each prediction by its quality, which is the survival time, and then sum and take the sign.
So, on the final, we'll get a new model.
You mean in prediction? In prediction, we don't get a new model, we get a prediction value. But now the prediction value depends on all the models that we learned, not just the final one.
Because I have multiple models.
Yes, we are using multiple models to get the final prediction. Okay? So we are keeping all of these models, actually. All of these models has to be kept to be used in prediction, not just the final one.
Dr. Flo,
Okay, did you understand it?
Yeah, but I think it's not practical.
Ah, that's another issue. We'll get to that. Okay, we'll get to that. Yes. Same type. Any question on how we use that? Yes.
So
We will be doing that. Hmm?
are we getting the average of the predictions of the one model?
Can you raise your voice, please?
Are we getting the average of the prediction?
It's like weighted average. Weighted sum. It's not average. It's weighted sum. Yes. It is exactly like in elections. Okay, in elections we give votes, right? But our votes are all equal. Right? Here, the votes are not equal. The votes are weighted by the quality of the model that is weighting. How do we measure the quality? Is by the survival time. If the survival time is large, then the vote of that model will get a large value, right? Because it will be multiplied by the survival time. Now that I hope that you understand how this works, then of course we need to keep track of the previous weight vectors and the biases, of course, and their survival times. Now, what is the problem with that? I think you started to think about whether this is practical or not. Why do you think this is not practical? Why do you think this is not practical?
Because if there are different models, they will have different options.
Fine, but the aggregate might be good.
For
That's
each
not a problem.
iteration- For each iteration, maybe it decides for something on one model, and on the other it decides something else.
Okay, it seems like you are confused still between training and prediction. In training, we are doing the same thing. We are not changing anything, except that we are just storing the models. Okay? In prediction, we are not doing iterations. In predictions, we are just getting a prediction from each of these models, and then we get a final prediction based on these multiple predictions. Okay? We are not doing any iterations in prediction. Okay? It's like let's say we have 5 models we learned in training. We are just getting the opinion of all of these 5. Now we have 5 opinions, right? We will weight every opinion and get a final opinion or final prediction from them. Okay? Type. Still, the question is, why do you think this is not practical? Yes.
Maybe because we're taking the opinion of the first models.
Okay, if the first models were good enough, their vote will be more important, right? We will multiply by how good it is. So, if they are not good, then their weight will be small. Type. Let's think about both phases. Training. Is there any problem in training? Fatma?
okay, we should keep track of all the previous models.
We are actually.
Storing them, yeah.
So that's the disadvantage, right? We need to store all the models. Okay? With small data set, maybe we will not have many models, but with large data set, we might have many models. Okay? So we'll have to store them. So there's a storage cost here. So we'll have to keep all of that in memory. Okay? So we store them. So we need a storage. Type. That's in training. How about prediction?
Wasting time.
Wasting time. It's not wasting, okay, but it needs more time, you mean. Okay? It needs more time. It's much, of course, slower than the vanilla Perceptron. Why is that?
Because it happens to
Why is that? So this one is slower. At least my opinion is that it's slower. Yes, because instead of taking the opinion of one model, we are taking the opinion of all models. If we have 1,000 models, it will be 1,000 times slower than the prediction of the vanilla Perceptron. Okay, so it needs more time. Yes.
That's it. In practice, do we actually care about the time? Because the CPS are
Very good question. Do we care about prediction time or training time? Which one you are talking about? Because these are different, right? Prediction time. Do we care about prediction time? It depends on what? On the application. Okay, it depends on the application. If the application the user is expecting fast response, then it matters. It is important. Okay, so prediction, of course, is important. Imagine, I know Google is not doing classification. يعني at least in the first look. But let's assume that Google is a classifier. Okay? Imagine that you write your query and then wait 1 minute, before you get the results. What will be your experience? It's bad experience, right? Not 1 minute. Let's say that you will wait 3 seconds. So you will count 1, 2, 3, and then the results come. Will you be satisfied? Of course not, right? Okay, so there are applications that the user expects very fast response. So you have to cope with that. Okay. Right. So we said that we have 2 problems here. We have the storage, right, in training, and we have the computation time in prediction. Wow. Okay. Right. How can we solve this problem? So voted Perceptron might give us better results than vanilla Perceptron, but it has this issue of the storage and the prediction time. Type. We will solve this problem, or we try to address this problem by making some approximations here. We try to avoid storing all the models. How? Now let's imagine that we removed this sign from the computations. First, the computation, the final values will be different or not? Probably will be different, right? Okay. But we don't care now. Let's assume that that will not be a big problem. But let's see if we remove this sign, what will happen for the computations. If we remove this sign, then that means that this computation will be like multiplying this survival time with the weight and the example, plus multiplying also the survival time with the bias, right, for each model. So we will have something like actually this. So here, this is when we remove the sign, and we can now rewrite it this way. By multiplying this with this, we have C times W, and then X. X is like a constant here, right? So we can get it out of the summation. So we'll have now a summation multiplied by X plus another summation, which is C times B. Okay? Type. How is that different from the previous one? It's just removing the sign? No. Actually, if you look at this summation, can we compute this summation offline, or do we need to wait until we get the example that we want to predict its label? Yani can we compute that in training, for example? While we are doing the training, can we compute it? Yes, it's just an accumulation. It's sum. Whenever we get a new model, we just add to the sum, the running sum, the multiplication of the survival time and the weight vector. And then when we get a new model, we just add its value. So we don't need to keep the weight vectors at all. We just need to keep that number over time. Whenever we get a new model, we just update that number. Same with the bias. So we don't need also to keep the bias. We just need to keep one number for that summation and another number for that summation. Only. We don't need to keep any weights, any biases. Just these 2 numbers. That would not be a number, by the way. That would be a vector, sorry. Okay, that would be a vector, because we are just weighting vectors here. But these would be numbers, actually. That would be just one number. So this is like, in vanilla Perceptron, we are keeping the weight vector and the bias, right? Here we will keep a weighted weight vector, or averaged weight vector, and also averaged bias, or sum of weights and sum of biases. Okay, it's just one vector here and one value here. And this is like now the model that we will use for prediction. So this is very now similar to the vanilla Perceptron in terms of what we want to keep from training. Type, what will happen in prediction? You see, this vector will be multiplied by X. There's no now sum over all the models, right? All the summations were done in training. We don't need to do any summation in prediction, khalas, right? Because we have this vector already, we have this value, we just multiply this vector by x and add this value. So it is like we are keeping just one model. So in terms of computations, this is exactly like the original Perceptron, right? We don't need to get predictions of multiple models. We are getting it inherently, okay? But we don't have to get them explicitly. And of course, after this, we do the sign as we do in the in vanilla Perceptron. Okay? So we don't need to store any models, any more models, except the final one, the final sum. And also in prediction, it's the same complexity or time complexity like the original one. Okay, so we avoided both. Type, what is the disadvantage? The only disadvantage here is that this is different from the voted Perceptron because we removed the sign. So the predictions here might not be the same like the previous one. So it's like a trade-off. If you need the voted algorithm, it is exact computations, but it's more costly. It takes more time. If you need an approximation that is fast, then you can use this. Okay? Is that clear here?
يعني في الواقع الفولت أحسن.
I cannot definitely say that. Okay, but one is an approximation of the other. Yeah, this one is an approximation of the previous one. But you can experiment with both. You can think of them as different algorithms now. Yes.
Can you read the disadvantage of the average?
Okay, what is the disadvantage of this one, right? What is the disadvantage of this one?
Doesn't take the sign.
Yeah, we remove the sign, so it's like it's an approximation of the previous one. It's not exact as the previous one. Yani, it will not produce the exact predictions of the previous one. It is just an approximation. But as Mariam indicated, that doesn't mean that it is worse. We can experiment with both, actually. Okay? Any questions on that? Do you understand now how we can apply each of the three algorithms? We have three algorithms now, by the way, right? The original one that we discussed in the previous two lectures, and then today we had two versions. The previous one called voted Perceptron. This one is called averaged Perceptron. Because we are not actually getting votes, individual votes. We're just averaging the weighted sum for each. Any questions? Okay, type. Does that solve the problem? I think we answered this question already. Now, let's switch to another subtopic in Perceptron, which is about convergence. First, what do you mean by convergence? If I told you that this model converged, what does that mean? Any idea? Have you heard about convergence, the word convergence before? Type. It has to have a meaning, right? What does that mean? Yes?
Different subcodes into one result.
Which means, so it's going to some, so it will get stable at some point. Okay? So it will get stable at some point. That's the meaning of it. Okay? So it will be fixed after some time. It will be stable after some time. That's the meaning of convergence. Type. The question now is, does Perceptron converge? Does it reach a point where it doesn't change? Now, stable means it doesn't change, right? After some time, it will not change. Will we have something like that with Perceptron? Will it converge? So that's a question. If it will converge, what does it will converge to? What will it converge to? Something that is good in terms of classification or not? And if it will converge also, how long it will take to converge? Because in training, we are starting with some model and we are changing it over time with the examples that we are going through and with the mistakes, right? how long it will take to converge, if it will actually converge. So we need to answer these questions. So as I said, convergence in the context of Perceptron means that it will not change, and it will not change in Perceptron means it will not make any mistake, right? So we define convergence in the context of Perceptron as going through one pass, one complete pass over the training data without training examples, without making any mistake. So it correctly labeled all the training examples. If it does that, then خلاص, it will never change, right? It will not make any mistakes, so it will never change. That's the definition of convergence here. Geometrically, that means that we found a hyperplane that will separate exactly the positive and the negative points, right? Because we said last time that Perceptron is trying to find, the algorithm of Perceptron is trying to find a hyperplane that will separate the two spaces, right? The two regions, the positive region from the negative region. So if it converges, that means that we found that hyperplane. Maybe we start with a hyperplane that's not perfect. We kept changing it over time until we find one that will correctly separate between the two regions, which means that it is perfectly labeling, perfectly predicting the label for all the training examples. So that's the meaning of it geometrically. So if we found a hyperplane that separates the positive and negative region, that means that it will converge on that plane, right? Now the question is, can Perceptron algorithm always find that hyperplane that will separate the positive and negative examples? So we started by saying convergence will happen if we find that hyperplane, right? And we all agree on that. The question now is, will we find it? Will it be possible to find that hyperplane always or not? What is the condition? So the question is, what is the condition? Okay? If you remember, to find that hyperplane, that means that the positive and negative regions are actually separate. The examples are separate, right? One in one side and the other is on other side of the hyperplane. That means that we have what we call linearly separable data. Linearly separable data is shown here in the left side example, which means that we can find a hyperplane that separates perfectly the positive examples from the negative examples. So this is an example of linearly separable data. Linearly separable means that it can be separated by a line or a hyperplane in general. This one is not linearly separable. We call it linearly inseparable. We cannot find a line here in 2 dimensions that can separate the positive from the negative examples. You will never find it. Okay? You can find a non-linear model here, but Perceptron will not find a hyperplane because it doesn't exist in reality. Okay? For this case. For that case, it is also inseparable. There is no way to find one line that will separate the positive from negative examples. Okay? So this case is linearly separable. These two cases are linearly inseparable. We cannot separate the two regions or the positive and negative examples by a hyperplane. That means that Perceptron will converge in this case, but will never converge in these cases, right? So it depends on the data. If the data is linearly separable, then Perceptron algorithm will eventually converge, or at least can find a model that will converge. In this case, it will never converge. But never converge means what?
It would always change.
And as we add, yes, it would always change if we do more passes. Of course, if we have 3 iterations and stop, خلاص, it will not change, right? But it's not perfectly separating. So in these cases, it will never. Even if we kept the number of iterations to infinity, it will never find it because it doesn't exist. Okay, so it will keep changing. Okay, and it will not converge. So if data is linearly separable, then it will converge to a weight vector that separates the data. It will converge to a model that will separate the data. If the data is linearly inseparable, then the Perceptron will never converge. It will never classify each point correctly. Okay? Yes.
اللي بيخلينا نقول ان البرسبترون هو linear.
Okay, go back to not the previous lecture, I think the lecture before, both lectures, and see how we found that geometrically. Okay, we mentioned that there is the weight and the weight vector and perpendicular to the model, so the model is always linear. Yes.
In this case, if we did not find the line, increasing the iteration number will help.
Will never help to find a perfect model because there is no perfect model. It's impossible. But it might give you good enough classifier, but it will not be perfect for the training data. That doesn't mean it's bad. Okay, that's a good question. Yani, not converging doesn't mean that this is a bad classifier. Okay, because maybe the data is not linearly separable because of some noise. Yani, for example, you see this data linearly separable, right? If I added 1 plus here, just here, it will not be linearly separable. Just because of 1 point. That might be even noise. There might be wrong input, wrong data, wrong example. Just noise. But because of that, Perceptron will never converge. But it might find this model, which is good enough. Right? So non-convergence doesn't mean it's bad. It might give you good classifier at the end. But here we are talking about convergence. Right. Now the next question is, how long does it take to converge? Now let's assume that it will converge. We said that the convergence condition is what? Is that the data set is linearly separable. Right? If the data set is not linearly separable, then it will not converge. Now we assume that it will converge. How long does it take? Right. To get to that, we'll have a couple of definitions. First, we will define what we mean by a margin of a data set with a specific model. And then we define the margin of a data set in general. First, the margin of a data set with a specific model. Here we will assume that we have a model that is separating. Here we are talking about a data set that is linearly separable. Okay? So we are talking about the margin of a data set with a model that is separating the positive from the negative examples. What do you mean by the margin here? The margin is the distance between the model, which is a hyperplane, and the nearest point in D. Let's see an example. Let's assume that these are the training examples. Positive, let's assume that this is positive and this is negative, for example. And let's first tell me if this data set is linearly separable or not. It is, right? It is linearly separable. We can find a hyperplane that will separate both types of examples. Type H1 is separating the positive from negative examples. H1. So the green line here, is it separating the positive from negative examples? Okay, so this is not separating. So we're not talking about H1. Type H2, is it separating? Yes, it is separating between positive and negative examples, right? Now we can compute the margin of that model with the data. What is the definition of the margin of that model with the data? It is the distance between the hyperplane. The model is a hyperplane, right? It's the distance between the hyperplane and the nearest point. Where is the nearest point to H2? Is it this point? Is it this point? Probably this is this point, right? So this value, this distance, is the margin of this data and H2. Okay? It is the closest, is it the distance between the model or the hyperplane and the closest point to it. Type, where is the margin of H3? H3 is separating also, right? Where is the margin of it? Probably this value. This is the minimum distance between the hyperplane and any point. Can we find smaller distance? You will never find a smaller distance. I mean, we will never find a closest point to H3 than this one, and maybe this one is the same. Okay, so that's the margin of H3. Type, let's think together what does that mean. Let me ask you a question. We see H2 and H3 are both separating the positive and negative points, right? Which one you think is better as a classifier? For the training, they are perfect, right? For training, they are correctly classifying all of them. So in terms of training, both are the same, right? They are perfectly classifying all training examples. They are perfectly separating them. But they are different models, right? They are different hyperplanes. Which one you think is better? And when we say better, what do we mean by better? Remember in the first lecture in the course, we talked about generalization. Okay? Which one will generalize better? Which one you think, if we used it in prediction, will be better? H2 or H3? H3. Why? Who said H3? Why?
Maybe because the distance is similar.
Similar between what?
Between
This one and this one, Yani?
yes.
What does that mean? No, that's not the reason. Okay, this is, yes, the margin of this is smaller than the margin of this. Akid, khalas, we know that. Why is that indicating that one is better than the other?
I feel like H2
H2
is overfitting.
is overfitting. Why do you think so? Type. Let me give you a hint. Okay, let's think together. If there is a point here, if there is an example here, okay, here, okay, what will be the prediction if we used H2? If we used H2, white or black? White, right? Because it's on the other side, right? Type. What will be the prediction if we used H3? Black. Which prediction is you think better? Should it be black or white? Black, right? Black, because it's closer to the black area, right? Black region, right? But H2 didn't get it. H3 got it. Why H3 got it but H2 didn't get it? Because H3 gave a bigger margin. Margin means it's like a separation between the two classes. Okay? So this margin, if I looked at this point, it is very close to the model. So the model might make a mistake with the close points, but it is less probable to make a mistake with further points. If the point is far from the model, it is more probable to get correct predictions. If it's close, it might be getting incorrect predictions. Okay, so this model will actually generalize better. Okay, because it is far from the positive side and far from the negative side. It's not close to one of them. When we are far from both sides, that means that we are in a safer location between both. Okay, so the points that will be close to the positive side will be predicted as positive. The points that will be close to the negative side will be predicted as negative. Okay, so H3 actually is better than H2. Yes, yes.
Can we say that H3 is better because it separates both regions equally?
Yeah, kind of, but you cannot say it's separated equally. Separated between what? Because the regions here are infinite. Yani, the region itself is infinite. Okay? So you cannot say it's separated, but you can say the margin, because the margin is defined to consider both sides. Okay? So the margin is large, which is good. Type. Now, the margin, now we defined the margin of a data set with a model, right? Now we can generalize that to the margin of a data set in general. The margin of a data set in general is the largest margin with any model. The largest possible margin with any model. Now we understand the definition of margin with a model, right? Margin of a data set with a model. The margin of a data set by itself is the largest possible margin with any model. So let's assume that these lines are all the possible models we can get. Then the margin of this data set is the largest margin among all of them, which is this one, right? Because this is larger than this one. This is actually not separating us. Okay? And if you look at this data set, you will never be able even to find a model with a larger margin than this one. Yani let's assume something like this, مثلا. This is separating also, right? What is its margin? Maybe this one, right? It's smaller than this. So the margin of a data set is the margin of the largest margin possible with any model. Okay? Type. My last question to you before we leave, assuming that you understand now what we mean by a margin of a data set with a model and the margin of a data set. If I have two data sets, one with very small margin and the other with very large margin, okay, which one you think it will be easier to find a hyperplane that will separate both sides? The one that with larger margin, right? Right? Why is that? Because if you imagine it, that means that there is a larger margin between the positive and the negative examples. If these are very separable like that, then it will be easier to find something in between. If they are very close, it will be very hard to find something in between that can separate them. Okay? So we'll start with that inshallah next time.